Ever feel like the world is telling you a story, but you can't quite read the words? Well, it turns out a lot of it is written in a kind of hidden language, the language of chemistry. It's happening all around us all the time, describing these amazing invisible transformations. And today, we're going to learn how to read it.
So let's just jump right in. What do these everyday changes, what do they all have in common?
Think about milk that's been left out on a warm day.
Or, an iron nail starting to rust in the damp air.
Or heck, even what your own body is doing right now to digest food. I mean, they all seem totally different, right? But believe it or not, on a tiny molecular level, they're all secretly telling the same kind of story.
And that story is the chemical reaction. And today, we're going to become fluent. Here's our game plan. First, we'll learn to spot these stories. Then, we'll learn the language chemists use to write them. We'll cover the one grammar rule you absolutely cannot break. After that, we'll explore the 4 main story genres. And finally, we'll see how all of this lets you read the world in a completely new way.
All right, let's kick things off with Section 1, Stories Happening All Around. So, what is this story they're all telling? Well, at their very core, all those changes we just saw are chemical reactions. That's where the very nature, the identity of a substance, fundamentally changes.
And this is the key thing to get. A chemical reaction is a true transformation. This isn't like water freezing into ice. I mean, it's still H2O, right? No. We're talking about a substance becoming an entirely new substance. That's when you know a chemical change has really taken place.
Which brings us to Section 2. How do scientists describe these amazing transformations without, writing a novel every single time? They use the special language of chemistry, and it's all built around the chemical equation.
Now, you could use a full sentence like this one. It's descriptive, yeah, but can you imagine writing that out for every single experiment? It's just way too long, way too clunky for a working scientist.
So the first step to simplify this is using a word equation. This is already so much better. On the left, you've got your reactants. Think of them as your starting ingredients. On the right, you have your product, the new stuff you formed. And that arrow just shows you the direction of the change.
But we can take it one giant step further to get a truly concise and universal language. By using chemical formulas, Mg for magnesium, O2 for oxygen, and MgO for magnesium oxide, we get this incredible shorthand that any chemist anywhere in the world can understand in an instant. This right here is the true language of chemistry.
But just like any language, this one has grammar. And in Section 3, we're going to explore its single most important rule, the one that can never, ever be broken. This is it, the law of conservation of mass. In simple terms, it just means you can't create or destroy atoms in a chemical reaction. Whatever atoms you start with, you have to end with. Think of it like baking a cake. If you start with 2 eggs and a cup of flour, you can't magically end up with 3 eggs in your cake. The atoms just get rearranged into something new.
And this law is why we have to balance our equations. Let's take the reaction of iron with steam, for example. As it's written here, it's unbalanced. It's illegal. We start with 1 iron atom, but end with 3. That can't happen. So we fix it by adding coefficients. To balance the 4 oxygen atoms on the right, we'll put a 4 in front of H2O. Okay, but that gives us 8 hydrogen atoms, so we need a 4 in front of the H2 on the other side to match it. Finally, we balance the iron by putting a 3 out front. Let's do a final check. 3 iron, 8 hydrogen, 4 oxygen on both sides. Perfect. It's balanced.
And here is our final perfectly balanced story. It tells us exactly how many molecules of each thing are involved. And you see those little letters in the parentheses? They just add another layer of detail, telling us the physical state of each substance. S for solid and G for gas. So we know the water was used as steam. It's a whole narrative, all in one line.
So now that we have the alphabet and the grammar, we can start to recognize the common plots, the genres of these chemical stories. Let's move to Section 4 to explore 4 of the most common types.
2 of the most fundamental types are perfect opposites. A combination reaction is basically a coming-together story, where 2 or more substances combine to form one single, more complex product. A decomposition reaction is the exact reverse. It's a breaking-apart story, where a single compound breaks down into 2 or more simpler things. One builds up, the other breaks down. Simple as that.
These little analogies make the 4 main types really easy to remember. A combination reaction is like a love story. Decomposition is a breakup.
Displacement is a switcheroo, where one element kicks another one out of a compound. And double displacement is a full partner swap, where two couples just switch partners. These four simple patterns describe a massive number of chemical reactions.
So, why does all this matter? What is the payoff for learning this new language? Well, that brings us to our final section, reading the world anew.
And this isn't just some abstract theory. This is the world around you. Respiration, the reaction that's powering your body right now by breaking down glucose, is a chemical story. The way whitewash hardens on a wall, the destructive rusting of a bridge, even the classic process of developing old black and white photographs. All of these are real-world processes described perfectly by the language you've just learned.
So this is the power you have now. You've learned the fundamentals of a language that describes the constant, invisible change that defines our world. You can now see past the surface of things to the atomic story happening underneath. So the only question left is, now that you can read it, what stories will you see today?